Well, welcome back. We're here at NASA Goddard with Dr. Claire Parkinson, a senior scientist here. When people think, Claire, of NASA, they think of the moon and the recent landing on Mars, but in doing some reading about some other things, there's a lot of things that NASA is involved with here right on Earth.
Oh, there sure are. There are lots of things on Earth that NASA is involved in. My specialty happens to be sea ice in the Arctic and the Antarctic, but there are other people here at Goddard whose specialty is hurricanes, others volcanoes, others sea surface, especially like life in the oceans, and then others would be vegetation on the land. All sorts of earth sciences as well as space sciences are done here at Goddard.
Well, that's interesting, and I didn't know that. I just thought of NASA as a space agency. Let's focus on the sea ice. What is it? Why is it important, and what's happening to it?
Okay, the sea ice is ice that's formed in the sea. It's floating around in the Arctic and in the Antarctic, so it's in both polar regions, and there's a lot of it. It's like in the wintertime in the Arctic, the area of the sea ice is about 1.5 times the area of the United States. And in the Antarctic wintertime, it's even more than that. So the big expanse of sea ice. Now, why it's important is that it has a lot of impacts both on the ecosystems in the polar regions, but also on the climate. And in terms of the climate, one of the biggest impacts that's really easy to understand is that when the sun's radiation comes down and strikes the sea ice surface. Sea ice is white. The sun's radiation reflects off. That's why it shows up as white, because it's reflecting most of the sun's radiation. When the sea ice retreats and goes away, and instead of striking the white ice, it strikes the ocean area, which is dark. The sun's radiation comes in, it goes into the ocean, gets absorbed in the ocean, and contributes to heating up the Earth system. So that's one strong climate impact that the sea ice has.
How is climate change affecting the sea ice?
Actually, we now fortunately have a really good record of that, because with satellites, we've had a satellite record of both the Arctic and the Antarctic sea ice since the late 1970s. That allows us to get the picture of the entire global region and to really be able to measure how the changes are occurring, whereas before satellites we didn't have that option. So since the late 70s, we've been able to see day by day how the sea ice cover is retreating or advancing, and every year it advances in the wintertime and it retreats in the summertime. So every year there's a big seasonal cycle. But over the course of the period since the late 70s, there's a lot of difference from one year to another, but there's a large trend, and the trend in the Arctic region is downward. It's a very clear downward trend, so that overall there's a lot less ice now than there was in the late 1970s.
So on average, you mentioned that in the winter it expands, but what you're saying is, on average, it's not expanding as much as it used to, and when it retreats, it's retreating even further than it used to.
That is entirely the case, yes.
Okay. How does this affect our polar bears?
Well, the polar bears, their traditional diet is centered on eating seals, and they get the seals by wandering around on the sea ice and then hunting the seals from the sea ice. When the sea ice retreats earlier and then stays away longer, there's a longer period that they can't be out on the sea ice hunting for seals. And so in some regions of the North Polar regions, such as Hudson Bay, the ice retreats all the way in summertime, so there's no more ice.
All the way to the shore.
Exactly.
Okay.
And so in those regions, the polar bears, they have no other option other than to retreat to land. Now, traditionally, they would have a few months then on land and basically wouldn't eat much during those few months. Well, now it's getting longer that they have to stay on the land. So they're having to rummage around. So the retreat of the sea ice is bad for polar bears, but you could look at it from the point of view of the seals and say maybe the seals have lucked out. So, I mean, the ecosystem is such that they're winners and losers.
Well, let me ask you, perhaps wade into maybe a controversial area here. We've talked about, just very briefly, climate change. Have any opinion, or do you know of any data that says, like, how much is contributed by man with all the fossil fuels we're putting into the air, and how much of it may be just an evolution of the temperature in the planet, which happens over different centuries?
Scientists realize that the climate is changing, but they also realize it's been changing for the past 4.6 billion years. In other words, ever since the Earth formed, the climate has been changing. So the fact of climate change is not controversial. Your other question, what contribution does man have, that is controversial. And in general, most climate scientists feel man is definitely having an impact. Exactly how much, different people would argue one way or the other. But there's several ways in which we're having an impact. And the one that gets a lot of attention now is that amongst the things that we pour into the atmosphere are so-called greenhouse gases. A greenhouse gas is a gas that pretty much allows solar radiation to come in and get to the Earth's surface fairly easily, but it blocks the Earth's radiation from getting out. So it keeps some of the Earth's radiation in the system that would have gone out otherwise.
And that's why the term greenhouse gas, because it's warmer. It gets warmer.
Yes, so it warms things up. Now, humans also pour into the atmosphere other things, such as little particulate matter called aerosols. And a lot of the aerosols have the opposite effect of cooling instead of warming the planet. The aerosols, however, people have been more successful in getting regulations to cut back on the aerosol input, and that's because the aerosols have direct health and impacts too, and it's easier to get regulations and laws passed to stop something that clearly is causing a problem. Whereas the fact that greenhouse gases are warming the planet is not perceived as anywhere near as serious a problem by many people in the public as the fact of like a huge pollution episode where hundreds of people might die. Then you get action. This happened in the 1950s. There was a huge pollution episode in London, and that led to a Clean Air Act in London, and following that came Clean Air Acts in many different countries. So that was easier to get legislators behind when there's something terrible that happens and you can identify the cause as human cause. With the warming, it's very different, because warming is not entirely bad. I mean, people could think of good things about warming. It means less deaths from freezing. I mean, so there's some good things about warming. The bad thing about the warming is that if we keep pouring as many greenhouse gases into the atmosphere as we are, the warming will become too much. So it's one of these things where something in moderation might be positive, but when you take it to the extreme, it becomes negative.
Excellent thought. I've got a couple more questions on that, but we're going to have to take a short break, so we'll be right back. Please stay with us. Welcome back. That was a very interesting clip. We've been talking about the North Polar ice expanding and contracting, but to actually see it happen is pretty fascinating.
Yes. Now, the reason we're able to see it so well with the satellite data is that the satellites are measuring not the kind of radiation our eyes see, which is visible radiation, but they're measuring microwave radiation, and the plus there is the microwaves that they're measuring can go straight through the clouds. So therefore, even when there's cloud around, you can still see your data at the surface. So what we saw in this clip was the expansion of the sea ice cover in the wintertime. So it was a particular year, it happened to be 2007, and we saw the sea ice expand outward until about the end of March, when it got out to an area about 1.5 times the area of the United States. And then it retreated in, and retreated until the middle of September. And then it expands out again. So this is what happens each year in terms of the basic seasonal cycle of the ice cover. Expands outward in the fall and the winter, and then it retreats back in. And the satellite data show us the details of how that's going on, and with those details we can see how it's changing from one year to another.
Well, that's fascinating. Is that what they would call time-lapse photography, for example? Then, or?
Well, in a way you could say that. Yes, you could say that. It's not exactly the same thing, because with time-lapse photography you've got a camera standing there and it takes a picture every so often.
Right.
With the satellites, they're actually polar orbiting satellites, so they're going around, and so as they get up, they'll get their data for the North Polar region, and then they're getting data all the way around.
It's not, if I get the term right, it's not a geosynchronous orbit,
it's not,
if I said that correctly?
It's not geosynchronous. Now you've got me saying it wrong, too.
Anyway, right before
it's sun-synchronous.
Sun-synchronous, all right. Right before that clip, we were talking about climate change, and you mentioned that perhaps a little warming isn't necessarily all bad, but is there some evidence or some theory that this climate change is also making some of our extremes more extreme, some more extreme storms, more extreme summers, more extreme winters? Because here in Maryland, it certainly seems like we had an extreme summer, for example.
There's a lot of uncertainty about that right now. Any individual year can't really attribute explicitly to the long-term climate change, and yet it's more the statistics of what happens overall. So there are a lot of uncertainties, and so I really don't want to say for sure one way or the other, although if warming continues to the extent that it's predicted, then the expectation would be, like with hurricanes, that you would be more likely to get more of the really powerful hurricanes.
We used to hear, and maybe it's still happening, we used to hear about that the ozone layer, there's be a hole in the ozone layer, and it was partially, I think, attributed to carbofluorides. You don't
Chlorofluorocarbon.
Thank you very much.
CFCs.
I don't remember reading much about that recently. Is that because there's less of it, or is it just not making the news? That is the hole in the ozone layer. You used to read about it every summer or something, and I don't remember reading about it.
Okay. The time of year that you're most likely to hear about the ozone hole is October. Late September and October. Now, the ozone in the ozone hole was getting less and less kind of dramatically in the 1980s. When this was realized, then people did take action, and there was an agreement called the Montreal Protocol in 1987, and that's been updated several times since then, and this regulates the CFCs that can be put into the atmosphere. This has markedly helped things in terms of like the trend of how deep the ozone hole is. It was going pretty dramatically, and it's kind of leveled off. However, it's leveled off in a way such that it's not like come back up to the ozone levels that had been there. So it's kind of leveled off, so you could still get like a record low for the ozone, even though there's been improvement. And therefore, if somebody reads that there's a new record low, they might think there's been no improvement. But the fact that it's no longer plummeting like it
Stop the
was.
slide.
Exactly.
Right, okay.
Shows that there was improvement. Now, people have modeled this situation in terms of the ozone hole, and they're anticipating that the ozone hole might get back up. It might be extinguished, or whatever term you might want to use. In other words, the ozone might get back to its earlier levels by about 2070 or so. But different models will predict different things, and it all depends on other things going on in the atmosphere also. But the predictions are that the ozone layer will recoup because we're no longer pouring the CFCs into the
All right, well, I'm
atmosphere.
glad to hear that one thing seems to be
Yes.
repairing itself based on our action.
It seems to be moving in the right direction.
We're going to take another break. We're going to have a clip coming up, so let's take a look.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of NASA's Aqua spacecraft designed to study the Earth's water systems. And everything continues to go well.
Plus 30 seconds.
30 seconds into launch at this time.
Roger.
Boy, Claire, that was pretty cool. Now, I understand that's called the Aqua Project, and it's a pretty big one, and it's something you've been involved with for quite a long time. So, for our audience, please kind of give them the basics of Aqua, what it does, and how you're involved with it.
All right, the Aqua mission is one of NASA's major Earth science missions. Aqua is a spacecraft and was launched in 2002. In fact, the clip that you just saw showed the actual launch. It was at 2:55 in the morning on May 4th of 2002, and it was very exciting to be there. It's always exciting to be at a launch. And as you could see in the clip, it went up into through a cloud layer pretty quickly, so we didn't see much after it got into the cloud layer, but just to see it launch after so many years of preparing for this satellite, it was very exciting. So the orbit that we wanted to get into, and that we were able to get into by launching at 2:55 in the morning, takes the satellite up north across the equator at 1:30 in the afternoon, which necessarily means it's coming down on the other side of the Earth, down across the equator at 1:30 in the morning.
Okay.
Then it comes up again. By the time it comes up again, the Earth has spun underneath. So the Earth has spun about 25 degrees of longitude, and the satellite comes up, and again it's 1:30 in the afternoon, and then 1:30 in the morning. So it's just each time it comes up, it's moving over to the west a bit, and that's why it's always coming up at 1:30 in the afternoon, going down at 1:30 in the morning. It's up at an altitude of 705 kilometers, and at that altitude, the length of time that it takes for a satellite to get around the Earth is 98.8 minutes. So it's all timed really carefully. So a little more than an hour and a half to get once around the Earth, and in that time the Earth has spun, and it's all called sun synchronous because it's always then coming up at the same time.
Now, I haven't had a chance to share with our audience, but Claire has a degree in mathematics. Somebody had to figure this all out. Was it you, someone else? Did they, in those days, did they still use slide rules, or did they have an early IBM PC? How did they calculate something like this?
Okay, I'm not the one who actually did the orbital mechanics or anything. That was other people. But they did figure out a large part of that way back before there were computers, but now we base everything pretty much on computers. We no longer use slide rules here. It's computers.
Claire, I understand we have another clip coming up of the Aqua satellite. Let's take a look. Well, that was pretty neat. Our viewers saw it. What exactly did they see? Because there were a lot of things happening in that last little segment.
Yes, indeed. What they were looking at was the Aqua satellite, the different instruments on it that are pointed toward the Earth to do Earth observations, and the fact that these different instruments have different scanning mechanisms. So some of the instruments are scanning back and forth like this as the Aqua satellite is moving along. That's called cross-track scanning. But others of the instruments are not doing the cross-track scanning. In fact, the one at the end where you saw a big antenna that was rotating around, that large antenna is actually rotating at 40 revolutions a minute, and it's collecting data in this more elliptical type of pattern. So the different instruments are scanning in different ways, and that's what that clip showed.
And the three instruments, for example, the antenna and the cross scanning here, they're measuring specific things, or what specifically are they looking for?
Okay, there are actually 6 different instruments on Aqua looking at the Earth, and they all have major things that they're measuring. One is an instrument that's specifically, well, it's called the Clouds in the Earth's Radiant Energy System, and it's looking at the radiation budget of the entire Earth. So it's looking at the radiation that's actually going out, so it's reflected from the sun and then what the Earth is emitting. Another instrument called the AIRS instrument, it's the 3 instruments that are kind of connected together in a system, sounders. So one's the AIRS instrument that stands for atmospheric infrared sounder, and then there are 2 microwave sounders that go with that infrared sounder. And those 2 instruments together are getting sounding through the atmosphere, so you end up getting temperatures at different levels of the atmosphere. Also getting a lot of the trace gases, including the greenhouse gas, water vapor, the greenhouse gas of carbon dioxide, and then other trace gases like methane and ozone. So it's getting trace gases as well as the temperature, and then there are two instruments that are really quite multi-purpose instruments, one measuring in visible light and one measuring in microwave light, and the two have very different pluses and minuses. They see a lot of the same things, like they'll see sea ice and they'll see snow cover and they'll see sea surface temperature, and they'll get measurements about all those things, but the one that does it with visible light gets much more spatial detail, but the one that does it with microwave light can get surface information even when there are clouds in the way and even when it's dark out. So got different advantages and different disadvantages of the different instruments. And the one that measures in visible light there also takes infrared measurements and gets information about life in terms of vegetation on the land and phytoplankton in the oceans.
The word aqua, does it mean water or associated somehow with water?
Yes, indeed. Aqua is Latin for water, and amongst all the many, many things that aqua is getting measurements of, included amongst that is a whole lot of stuff about water in the Earth system, including water in its vapor form, water vapor in the atmosphere, water in its liquid form, which would be like the ocean surface plus soil moisture on the land, plus liquid water in clouds, and then also solid water, which would be ice, and that would include sea ice in the oceans and include land ice on land, and also ice particles in clouds. So all those things are being measured by instruments on the Aqua satellite, and also all sorts of aspects of the so-called water cycle. So the water cycle is where you've got like water evaporated from the ocean, gets up into the atmosphere, moves around in the atmosphere as water vapor, condenses into liquid particles, becomes visible as clouds in the atmosphere, then precipitates. All those things are being measured by the Aqua satellite.
Any last thoughts before we go?
No, but it's been very nice talking with you, Steve.
Well, Dr. Claire Parkinson, it's been wonderful having you on the show. That's our show for today. Thank you very much for watching. Please watch again next time.